Hello everyone, welcome back to alkaline hydroxide 784, and today in the physics series we are doing wave motion. So we will detail a bit on the stationary wave in the appropriate part of this video. Sorry about the previous episode ending. So I'm just going to once again go through the learning outcomes and tell you what I can tell you about it. Yeah. So the first thing to know is that wave motion is like the chapters of 10, 11 and 12, oscillations, wave motion and superposition, are quite connected, so they're like a sequential kind of order to themselves, and therefore you should understand these three topics as a whole and see how they're connected with each other. Okay, so now let's look at the learning outcomes. The first one is about the terms displacement, amplitude, period, frequency, phase difference, wavelength, and speed. Okay, displacement. Okay, we already looked at some of these terms in another chapter. I believe that was the one with um, the one with the motion in a circle or something, that kind of stuff. So let's look at this in terms of waves instead. Okay, so the displacement would be the distance that the wave travels from the origin point. So if you think about it, like maybe your wave source is at point 0 and the wave is has traveled about 1 meter in a particular direction. So that is your displacement of the wave. You can also talk about the displacement of the particles in the wave, but yeah, that is more for the question, like on what the question answers in the sense. Okay, so the amplitude is the, of course you know what the amplitude is. It is the maximum displacement of a wave particle within, if you look at waves where the particles don't move but only the energy is transferred, the particle is the one that has displacement and it has a certain amplitude, the maximum, the maximum that it moves before it goes back to the center point in a sense. And if you're looking at waves where even the matter moves along with it, it's kind of like the same thing. It's more of the distance between the crest or the throw point and the center area. And the period of the wave is the time taken for one wavelength to happen, I guess. And frequency is the number of wavelengths within a second, and it's in the unit of hertz. And phase difference here will be if you compare two different waves and they are slightly different from each other, you can take, let's say, the point of the particle on each of the crest and see what's the difference between what's the distance between the two of them, and compare them to the wavelength distance and see what is the phase difference in that sense. And of course the wavelength is the basically the distance that a crest and a throw covers, and the speed would be the the distance a wave can travel within a certain time period, for example per second. So yeah, so from definitions of speed, frequency and wavelength, we have a certain equation. So how does that work? um we know that the speed of a wave is the distance that it travels over the time taken for it to travel. So in our scenario, we will use the wavelength as the distance that it travels. And if you think about it, the period is the time that it takes for a wave to travel one wavelength. And if you put wavelength over period, it is equivalent to saying frequency times wavelength, and therefore you get the equation speed equals to frequency times wavelength. And I think you guys will remember this equation very well because it's pretty simple. It's just V equals to F lambda. It's very easy to remember. So just remember that equation very well and you'll be good. So Yeah. So just remember this equation and use it for whatever question requires you to use it. And if you look at light waves specifically, instead of using just any generic speed, you would be using the speed of light, which is 3 times 10 to the power of 8. So do keep that in mind when you're looking at electromagnetic waves, whether, or it can be like visible light, or it can be like so-called infrared or UV or anything within the electromagnetic spectrum. They all have the speed of c, which is 3 times 10 to the power of 8. I do not know why I remember that so well. Okay, it's actually in your data list, like the speed of light, so don't worry about forgetting it. You'll be fine. So yeah, that's for point B and C. So point D, understanding that energy is transferred due to a progressive wave. Okay, so in a progressive wave, let's say you have a sound traveling through the air. Do you think the air moves along with the sound? Of course, the air will move, and that's why the sound can actually move through the air. But the air doesn't like suddenly go 1 meter away from, like, this particular molecule isn't gonna go 1 meter away from where it was just now. It will somewhat come back to the same area that it was after the sound has passed through. And therefore, in a progressive wave, energy is the thing that's transferred, not really the matter itself. But if you look at a water wave, the water itself is being transferred to the front. That's why you somehow get the wave creeping up on the beach. It's not just the movement, but the water itself gets onto the beach. So there's a difference between a wave where only energy is transferred and a wave where the matter is being transferred. So a wave where energy is transferred is called a progressive wave, and when energy is not being transferred, it is uh, it is a stationary wave. It stays in the same area. So this a stationary wave would be something like the one that we saw at the end of last episode, the one that you can form within a pipe or a string, because you're restricting the movement of the wave to those 2 points, so the energy cannot be transferred. And it's more of just a string moving up and down and up and down and up and down forever and forever. So there's no transfer of energy to other areas of the system. Okay, so point E, the relationship of intensity and between intensity and amplitude. Okay, so if you think about it, like, if your light is brighter, that means it has a higher amplitude. Or if your sound is louder, like if I talk with a really loud voice versus talking with a really soft voice, if I look at my audio recording, the loud voice will show a higher, you know, like a higher amplitude compared to the soft voice. So likewise, your intensity of light or your sound or whatever it is somewhat related to the amplitude of that wave. So what exactly is the relationship? It is that intensity is proportional to the square of amplitude. Okay, why is this the case? Well, I don't know. Okay, I guess the fact that intensity increases with amplitude is pretty obvious, but the fact that it's a square law would be more of because of the way that waves can transfer. If you have like a point source and you're transferring in all directions, you imagine it in terms of an area. So the area is a square, like it has 2 dimensions to it. So there's a square aspect to the relationship. So it would make sense to say that intensity is proportional to the square of amplitude and not just to amplitude itself. Instead of, like, the power is 2, not 1. Okay. So please do remember this. There's a square law to this logic. Okay, so yeah. So the next point is about the wave from a point source. Yeah, traveling without loss of energy, inverse square law. Okay, yeah, this is what I was talking about. So if we have a wave that is moving from a point and is moving out, it yeah, we look at it in terms of the inverse square law, because the let's say you have a certain area that you're looking at. So the like the the wave will move in one dimension, like each wave has its own single dimension, and the area that it covers will be different, because as the wave travels further and further, if you imagine a sphere at the center, the sphere becomes bigger and bigger and bigger. So the area that the wave has to cover is much larger. And since the same like intensity, or the same amount of that wave has to cover a larger and larger area, the intensity will decrease in a square law, in a sense. So actually this is not really related to the intensity and amplitude square thing. It's a different logic. It's that with distance, the intensity decreases in a square-ish way. You know what I mean? Like, let's say if the wave is of intensity I at the point, at point 1, and it moves like, I don't know. Okay, at point 1 at 2 meters it is intensity I, and at point 2 at 4 meters, what's the intensity? Since the distance is twice, the intensity will be 1/4 that of the intensity at point 2. So just, sorry, at 2 meters. You get what I mean? Yeah. So that's the inverse square law. So intensity is proportional to 1 over distance squared. Okay, so analyze and interpret graphical representations of transverse and longitudinal waves. Okay, so how do you remember what's the difference between a transverse and a longitudinal wave? Because sometimes we mix them up, like we forget which is which. Well, think about it this way. If you're looking at a transverse wave, like when you say transverse, you can think about the think about the universe. Think about the fact that light can go through like pretty much near vacuum areas, versus sound, which requires some kind of medium to transfer to, and that was a longitudinal wave. Okay, that obviously this is not the actual meaning of transverse and longitudinal, but it might help you remember which is which. I don't know. So light is a transverse wave and sound is the longitudinal wave. So transverse, like light or EM waves, well, if you think about it, when they move, like if they move, how to say okay, like the energy transfer is parallel to, is it parallel? I don't know. Wait, I need to remember which is which. One of them is parallel and one of them is perpendicular to the motion of the particles. So when you speak with your mouth, the sound vibrates the air particles parallel to it, and therefore the sound is transferred. But when you use light, the light just can go in many different directions perpendicular to the move. Yeah, like the energy transfer is perpendicular to the movement of the wave. So you can use the entire axis of rotation and you get the same logic to it. So if you want to look at it visually, right, light, you can imagine the middle axis as a line. And for light, when you draw the wave, it is actually the motion of the the energy in a way. Versus for sound, if you draw the wave, that's not really the motion of the air particles itself. The air particles are actually moving within the axis, they're not moving up and down. And the energy itself isn't moving up and down, it's more of moving parallel to the axis that is going on. And therefore light can move in many different planes as long as the plane is perpendicular to the axis itself. And that's why you can do something called polarization with transverse waves. So, okay, so if you were to write a definition, you would say for transverse wave that the energy transfer is perpendicular to the direction of motion of the wave, and for longitudinal it would be parallel. Okay, so polarization, what would polarization be? So for polarization, you would require that it is a transverse wave because it allows you to selectively choose all of the waves within a certain plane instead of choosing all of the other waves that can come in all the other planes that are perpendicular to the axis. So this doesn't work with sound because sound waves only go in that one direction. They don't have like multiple planes that they can travel in. So with polarization you can make a nice um you know nice beam of light that is nice and straight and is within one single plane. So how do you, like, if you think about it, when you put the polarizer in front of the light, since some of the light will end up being blocked by the polarizer only allows certain planes to pass through. What's the intensity of the light after it passes through the polarizer? It will be decreased quite significantly, right? So the first time that it passes through a polarizer, if the polarizer is like uh it's like the first polarizer, it and the light is unpolarized, the intensity will decrease by 2. Do remember that, because when the light is unpolarized it is in all directions already, and therefore you can, no matter which how rotated the polarizer is, your intensity will only decrease by half. But after that, you have a certain plane of light, a certain polarized light. And if you want to see how much of that light will pass through another polarizer, depending on its rotation from the axis, you had to use something called Mallucis Law, which is intensity is proportional to cosine square theta. So how would that work? Basically, if you think about it, the the plane of light is in one certain direction, and when you rotate it there's a certain angle that you get to it, and therefore you would use some kind of trigonometric function to get the the intensity after passing through that particular polarizer. And we use, if you think about the amplitude itself, we can use like some trigonometry and we get the cosine theta as our new amplitude. And since amplitude squared is proportional to intensity, intensity would then be proportional to cosine squared theta if amplitude is proportional to cosine theta. So yeah, that's how it works. That's a simple way of saying it that doesn't really make that much sense, but okay. So the point is, remember to use this particular law, which is that if you want to find the intensity of a plane polarized light when it goes through another polarizer, you would have to use this particular you know intensity proportional to cosine square theta. If you are scared that you end up thinking of sine square theta instead of cosine square theta, think of it this way: if the polarizers are perpendicular to each other, there will be absolutely no light passing through after that. So at 90 degrees, which one is actually 0? Is it sine square theta or is it cosine squared? Is it sine 90 or is it cosine 90? Well, it's cosine 90, right? So use cosine. Simple as that. Use that to rationalize using cosine. Don't accidentally use sine because that wouldn't make sense. If it's parallel, there'll be no change in intensity, so that also agrees with cosine instead of sine. Okay, so the next point is about the frequency of sound using a calibrated oscilloscope. Okay, so some of you may have actually seen an oscilloscope in your physics lab. But usually what they will do is they will just print some funny diagram in your exam paper with some waves on it, and they'll ask you to read it. So the idea of that is that one of the axes will be the time frame or some other frame, based on, you had to read the axes to make sure you know what you're doing. And the vertical axis will usually be the amplitude or something like that. So when you look at the printed diagram that you see in your exam paper, what you need to take note of is the value of each square. So you can actually, if you use an actual oscilloscope, you can adjust these values. You can make each square equals to some certain unit of time or something like that. And so when you're doing your question paper, please take note of the value of each square, and also the things that the axes are determining, in the sense, the variables x and y. And from there you can answer the question pretty easily. It will usually be something related to the wavelength or frequency or something like that. So just use your v equals to frequency lambda. So yeah, that shouldn't be too hard to do if you know what the calibration is. Okay, so the final point in this topic is determining the wavelength of a sound using stationary waves. Okay, in the previous topic, we kind of looked at the strings and air columns, and it turns out that that thing is only covered in superposition. So let's just go through very briefly on how the wavelength of the sound can be determined with a stationary wave, and we will look at that thing again in greater detail in superposition. So for a stationary wave, what exactly is it? As we saw in the previous episode, it will be something where the wave will just stay in one location, like it doesn't move anywhere, there's no energy transfer whatsoever. So for example, if you have a string or you have a pipe where the sound is okay, since you're looking at wavelength of sound, we would usually expect it to be in a pipe, for example, and the sound will be traveling within that pipe for as much as we can possibly as much as it can. It cannot escape the pipe because of the pressure of the air outside, and the open ends will be like the nodes of the stationary wave. So what is the wavelength of that wave in a stationary wave? It would be something like if you think about it, a wavelength is just one crest and one throw. So it would be the distance between two nodes, and you times that by 2. Because between two nodes you get a crest or you get a throw. So if you get the distance between two nodes and then you times it by 2, you will get the wavelength of a stationary wave. Or if you have the length of the pipe or something like that, you can then see how much of the wave is in that pipe, like how much of a wavelength is in the pipe, and accordingly you can find the wavelength of the sound. So I think that shouldn't be too hard to do. We will look at it in greater detail in superposition. It turns out that I talked about it way too early, so it's supposed to be actually talked about in superposition, the pipe and the string example. And yeah, so I think that's about it. You can then go and continue on with the next topic in superposition, which will come next week. So yeah, good luck to your studying. Hope you found whatever I told here useful and somewhat clear enough to understand. If you did, please press the like button and subscribe. And oh yeah, by the way, I just have some updates. You can look forward to Project Uni update, another set of videos from Project Uni, and potentially some other interesting videos before I start the next series, because the math series is over and we will be probably doing another different subject after covering special episodes or special things that videos. So hope you're looking forward to that, I guess. So with that, I would like to say thank you and bye.